Today, I'm going to talk about a new metadata index system that is designed for cluster storage. This is a joint work among University of Washington, University of Michigan, and Nutanix. Our work targets at today's enterprise clusters, which comprise of tens to hundreds of nodes, and they are mainly used as private clouds to perform on-premise computing, and they support virtualized execution of applications. Customers initialize virtual machines running different kinds of workloads, including legacy ones, and the virtual machines runs on one or several virtual disks that is provided through the cluster block storage systems. The virtual machines performs reads and writes to the virtual disk blocks, and they are translated through the cluster block storage systems to relative access on physical disks that contains the virtual disk block. So for such a metadata index systems, which is the key component of the cluster block storage systems, the translation between virtual disk blocks and physical disk blocks are done through 3 levels of maps, and I will outline below how this works. So the virtual disks contains a sequence of extents, and the extents are shares across different virtual disks. And the system using the virtual disk block map to map from the virtual disk offsites to extent IDs. And the extents are grouped as large segments and translated through the extent ID maps. And then the extent ID groups are saved as continuous physical storage systems on the storage device. And the reason why there's multiple mappings works in the metadata systems is to support virtual disk features such as cloning, and also to accelerate the virtual disk access performance. So essentially, the metadata maps is a key-value store systems. Just like the overall systems, it should provide high performance and strong consistency in the presence of failures. And the mapping layer should be durable to minimize the probability of data loss. And this indicates that the metadata should be committed to stable storage before acknowledged back to the clients. And generally, a metadata map supports 4 kinds of APIs. So create the key-value pairs, delete the particular key, read the value of the key, and update the key-value pairs. So we support compare and swap instead of normal writes. So compare and swap is a synchronization primitives according to Henry's impossibility and the universal hierarchy. Providing CAS is as challenging as solving the consensus issues. And also, most of the metadata operations in our systems are read, modify, write updates. Therefore, CAS is more suitable in our scenarios. And furthermore, we provide CAS so that it can enable at most once execution schematics without maintain per client execution states. So a traditional approach to realize such a metadata index systems is to build a sharded and replicate key-value store systems. In particular, we'll partition keys into different shards and use a DHT to map shards into different replica sets. And then within any given shard, we will use a log structure merge tree to build persistent key-value store systems. And then to make the system fault tolerant, we will take the Paxos protocol to make multiple data copies consistent across different replicas. Now let's look at the baseline system design. As I mentioned, it's using Paxos protocols to agree on a sequence of commands across different replicas. So for any given shard, one of the replica will become the leader. It gets a request from clients and then send an accept message to all the replicas. And after receive a majority of accept acknowledgements, then it will write the commands into the Paxos log, which is saved in the stable storage. And then the leader will send a learn message to the followers to indicate the command is chosen. And then all the followers will execute the command following the commit order. And next, the leader and also the followers, after receive the learned message, will run the command locally. And in our case, which is the log structure merge tree read and write. Generally, a log structure merge tree comprises of in-memory mutable memory table and disk resident immutable access tables. For write operations, it updates the memory table and commit log. When the memory table reaches a set limit, it will dump to the level 0 access table through many compact operations, which further merge to low-level access tables through major compact operations. And for read operations, the requests are served from the memory table or low-level access tables if they are missing from the memory table or high-level access tables. And after the command is executed, then the leader will return the results to the client. In such a systems, one can eliminate the commit log because the Paxos log also saved command history. So the baseline systems has satisfied our design goals. However, it brings in 3 performance issues. So the first issue is that each node maintains multiple shards, and each shard for one replica groups. If there are 3 replicas sharing one SSD systems, then each replica will create one shard for the SSD. And if there are 2 SSDs in the systems, then the replica groups will create 2 shards, one for each SSDs. And this enables balance the shards to SSDs in a flexible way. However, because of long-term and short-term access skews, one would see significant load imbalance. So in our characterizations with 6 shards, most loaded shard will receive 4x more IOs than other cases. The second issue is the high tail latency because of the head-offline blocking problems. Because commands have different execution costs. Consider log structure merge tree read operations. If they are served from the memory table, it takes a few microseconds. But if they are served from the low-level access tables, it takes at most hundreds of microseconds. Therefore, there is a huge skew in access latencies. However, we have to process the commands following the package log in order. One would see head-offline blocking problems. So the tail latency of fast operations will become worse because of some slow operations ahead of it, no matter whether the operations are accessing the same key or not. So consider the example here. Operation 2 will slow down the execution of all the following operations. And then the last issue is the suboptimal batching from different shards. For SSD systems, batching improves the SSD write performance. It can amortize the fixed cost of preparing a write operations and effectively use the SSD internal parallelisms. However, when there are multiple shards coexist in the systems and there are load imbalance across different shards, this will cause many small writes, which reduce the possibility of consolidating large writes. As a result, it will break the batching efficiency of the underlying storage device. And in our categorizations, we found like 1 consolidated log per SSD outperforms the sharded case by 1.6x in terms of throughputs. So to address these 3 issues, instead of representing the whole shard as a replicated system machine, we developed a system that using fine-grained replicated system machine where each key value pairs is on RSM. Now let's look at how FRSM can address the performance issues as I mentioned before. So firstly, FRSM enables flexible and late binding of operation processing to any CPU cores and SSDs. So any key value pairs can be processed on any cores as long as it provides in-memory synchronization primitives to deal with the concurrency, and any batch updates can go to any SSDs. As a result, this enables balanced use of the CPU and storage. And second, FRSM only requires per key ordering instead of per shard ordering. As a result, it can eliminate many unnecessary head-of-line blocking cases. And in the example I mentioned before, with FRSM, the operation 2 will only slow down the execution of operation 3 and 5 because they are accessing the same keys, and operation 4 is not stored. And finally, FRSM enables better batching. Compared with the traditional approach that represents each shard as a log structure merge tree, FRSM consolidates all the key value pairs in a single consolidated log structure merge tree, and the unified logs will strip across multiple devices, which enables effective batching of the IO request. So these are all sound good. However, to realize the idea is not trivial, because FRSM is actually heavy-weighted operations. Each replicated system machine has its own operation log, and it requires an explicit leader election phase. If integrate such logics at the per-key granularity, it will introduce lots of overheads. To address this challenge, we employ 3 techniques. Firstly, we take advantage of the key value object property to remove the text log. So the observation we make here is like, for key value objects, the next consensus state is a function of the current consensus state plus the ongoing operations. Instead of maintaining the log history, we can only maintain the current key value as well as the ongoing operations. And secondly, we take advantage of the workload execution characteristics to further reduce the consensus state. So the observation we make here is like for comparative swap and read, they can be speculative execute. Therefore, instead of maintaining the currently stable value, only maintaining the speculative value is good enough. And in this way, we can streamline the consensus states to include just the operation number, the prepared proposal number, and the accept proposal number. And finally, we take advantage of the failure characteristics of the managed cluster to reduce the frequency of per-key leader chains. Next, let's see how does compare swap and read works in the FRSM case. So request first come to the leader. So in FRSM, the leader is the logical initiator of the operations, but it may not get the ownership of the key because each replica can become the leader. And it can previously issue a write operations and maintain the current proposal number. Therefore, we perform LSM read operations to check if the prepared proposal belongs to the leader. So in our case, we use shard level leader to indicate who can initiate the operations, but then we rely on the key level promise number to indicate whether the request can go to the fast path or not. So if the leader have the ownership of the key, then the requests are go through the fast path, which is only the accept phase of Paxos. However, if the leader doesn't own the key, then it will go through the slow path. And during the prepare phase, it will propose a higher proposal number. So the consensus state is saved along with the key value pairs, which are further compact into the SS tables in the future. And in FRSM, we propose different reads to handle different situations. So in the normal case, we will perform column read. That is, pulls from a column of nodes. If all the nodes in the column have seen the most up-to-date values of the key, then the leader will return the result directly. However, if there is no most up-to-date value to the key, then one needs to propagate this value to the column nodes. As a result, in this case, we will perform a mutating column read. In our case, we use the consensus state to determine the possibility of whether an update lagging in a partitioned or failed nodes. One optimization applied in FRSM is the leader-only reads. This is enabled with a shard level scan in the background and the leader leases. So when it checks the leader has all the up-to-date key value pairs, it will enter the leader-only read states. And during this phase, during the least valid phase, it can handle all the read-write requests through the local memory table and SS tables. So FRSM has more features, and in the paper we talk about how to provide bounded transporting processing that allows clients to reason about the execution status of recent commands. We also take advantage of the log structure merge tree for faster recovery when handling transist and correlated failures. And we tweak the replication factor and at minimum forwarding states to reduce the state transfer when node joins and leaves the systems. And finally, we add a tombstone record for reliable key deletion. So in terms of evaluations, we first perform characterizations over 980 customer clusters. And our characterizations focusing on understanding the key access popularity, the value sets distribution, and the read-write ratios. We then evaluate FRSM in both controlled and real-world execution scenarios. In the controlled experiment, there is 4 Supermicro servers, and each server with 2 Intel data center scale SSDs. Then we build a customized workload generator that generates key value pairs based on our categorizations. And we compare FRSM with the traditional approach, which is the sharded-based replicated state machine, short for CRSM. And to understand how the FRSM works in the real case, we report the node and cluster throughput from the metadata layer of the systems. And we collect failure data from the customer clusters. The following experiment consists of 12 shard systems across 3 node replicas, and each node have 12 cores and 2 SSDs. In the CRSM case, each node is the leader for 4 shards, and each shard runs on dedicated cores. And in the FRSM case, all the key value pairs can be processed on any cores. And there is a unified lock across 2 SSDs. And we consider the uniform case and configure the CRSM with different batch size. So apparently, large batch helps improve the throughputs, But for CRSM case, it only helps a little bit because there is still 12 shards in the systems, which breaking the batching efficiency of the underlying storage device. So compared with FRSM, we achieve 2.3x better throughputs. And the performance benefits come from 3 facts. So firstly, we allow requests accessing different keys to be reordered and committed when they are complete. And also, we can reduce the computation cost of scanning the Paxos log and retry the uncommitted entries. And finally, we can eliminate some unnecessary head-of-line blocking problems in our situations. FRSM can also achieve better load balancing. We use the same experiment setup and vary the number of CPU cores. And in this experiment, we consider skewed case and configure the CRSM with 64 byte size. So when there's 12 cores, FRSM can achieve 11.1 better throughputs. And for CRSM case, it can achieve no more better throughputs with more than 2 provisioned cores. And this is because like FRSM enables flexible and timely executions of requests that accessing different keys. However, in the CRSM case, all the request has been checked into the Paxos log, which is subject to the skews, access skews, and head-of-line blocking issues. So FRSM is deployed at the metadata layer in the Nutanix cluster architectures over many years. And the metadata layer serves as the basics for many other system components. And in the paper, we have more results about real-world performance, such as the throughput and the real-world deployments, the leader-only performance benefits, the cluster failure rate and recovery performance, and the leader change overheads. We also evaluate the background scan performance that can enable the leader-only reads. With this, I'd like to conclude the talk. So in this work, we present a consistent and fault-tolerant metadata store for cluster storage systems. The key idea behind the system is the fine-grained replicated state machine, which reduces the load imbalance, improve batching efficiency, and minimize unnecessary stores. To enable the systems, we co-designed the consensus protocol with the data store. We add minimum consensus state into each key value pairs and streamline the operation processing of the per key replicated state machine. We demonstrate the performance benefits in both controlled and real-world execution scenarios. Thank you very much for listening. I'm happy to answer any questions.
Question for Ming?
I have 2 questions. The first one is, how often do you see this head-of-line blocking issue in production? Does it happen very frequently? And what's the reason it's happening? Is it because some random network latencies, between the Paxos nodes, or is it because of a certain Paxos transaction is too heavy? That's my first question.
First question, okay. So the first question is, how often does the head-of-line blocking problem happens in the systems? So we perform the characterizations using controlled experiment. We don't have particular results from the production trace to show how frequently the head-of-line blocking problems will happen. And I can say about some reasons about the head-of-line blocking, why it happens. So as you mentioned, the networking latency is not the major reason. The major reason is because of the key access popularity, because you have to process the request follow the Paxos log order. Therefore, when 2 requests come into the same key, then you will see head-of-line blocking issues.
Okay. All right. My second.
If I may ask you to hold on to the second question so that we get another question.
Oh.
Thank you.
Sure.
Thank you.
So I can wait after this.
Ask it offline if you don't mind.
Oh.
Thank you.
Hi, Marius from UBFL. Thank you very much for the talk. So there is a big design space between having one shard per core and having one state machine per key. I'm curious if you try to experiment all this design space. So did you try to increase the number of shards gradually till you go to one state machine per key?
Yes, so the question is like with more fine-grained, does it help improve the performance of the systems? In our controlled experiments, we actually go through more shards, and for both skewed and random cases. And we show like FR7 can both improve the performance of these two cases.
All right, let's thank Ming one more time.